So we near the end now. There is much more that could be said on almost any topic we have covered so far, but we have to draw the line some point. I do want to make some final comments here on a few matters that we've touched on before in some cases, but want to highlight them a little bit more. We'll also have a summary for week 8, of course, and I'll do a summary video for sort of the whole course, not everything in the course, but some of the key concepts, a roadmap through the course, our journey through the course, as it were. So I want to do 4 things here under final comments. First one is the role of crucial experiments. I believe along the way I mentioned the experiments of Walter Kaufmann, who was actually spelled with only one F. Many times you say it with 2 Fs, but Walter Kaufmann, German experimental physicist, and in the years after the discovery of the electron in the late 1890s, he and others were doing experiments figuring out what was known as the charge to mass ratio, E being the charge of the electron, M being its mass. And he especially focused on what happens if you shoot electrons at higher and higher speeds. And he shot them through various electric and magnetic fields, and because they had a charge, when they go through an electric field, there'd be a deflecting force, so they move in certain directions and certain distances. And then in a magnetic field as well, a moving charge would feel a force on it. And because the theories, the understanding at the time said that charge did not vary with velocity, and still doesn't, but the idea was mass does because of Einstein's equation. And there were others who had similar ideas like this just from the experimental results. But one way to interpret, remember Einstein's energy equation here, gamma mc squared, is that if you look at this part, you can say that's what's sometimes called the relativistic mass. And it changes with velocity by the gamma factor here. Now, in more modern terms as it developed, usually we think of the mass just as the rest mass, and we don't think of the mass actually changing with velocity, but think of the energy changing with velocity. But you can also think about it in terms of just the mass increases with velocity. That's often, often hear that said about one of the results of the theory of relativity is that at higher and higher velocities, the mass of a particle actually increases. And so that's what Kaufmann was looking at here. He was saying, okay, the charge is going to be constant, is not going to change at higher velocities, but the mass will. And therefore, you could do various measurements. And out of these results, he started, had a series of experiments in 1902, so even before the miracle year of Einstein, even before the special theory of relativity, there were other people working in these areas, as we've mentioned before, but coming from very different directions than Einstein eventually did. 1902 he had some, and then in 1905 a more accurate series of experiments. And at the end of those experiments in 1905, he said this. His result was, the prevalent results decidedly speak against the correctness of Lorentz's assumption as well as Einstein. Lorentz, of course, had his own ideas and theories here that were similar to Einstein. Remember, that's why we call it the Lorentz transformation, or transformation equations. And basically, Kaufmann was saying, my results here are pretty definite, and they speak against sort of the Lorentz-Einstein way of looking at things. And interestingly enough, what happened is really nothing as far as Einstein was concerned. Max Planck actually looked at the data a little bit more, did his own reanalysis of the data, and said, well, it's not quite as definite as Kaufmann maybe makes it out to be, but seems to be getting pretty good data. Einstein himself, however, said this in 1907. You may remember he wrote, I've mentioned, a review article on the theory of relativity. And in that, he analyzed some of Kaufmann's experimental results, gave those results. And Einstein basically said is that even though these results favored some of the alternative theories in the model of the electron they were trying to create at that time, he said that they were unlikely to be correct. The alternative theories were unlikely to be correct, even though the data seemed to fit them better, because they were less general than his theory was. They were more ad hoc, and so on and so forth. So even though the data seemed to be against Einstein's theory of relativity, he said, nope, I'm going to stick with the theory. It wasn't actually until 1914 that things got cleared up, and they're able to figure out that, yes, there were some subtle errors in the data here. So that's one so-called crucial experiment, because often we have this idea in science that you have something like somebody has a hypothesis, like Einstein did, then you make a prediction from that hypothesis, and then people do some experiments, and perhaps the prediction is refuted. So essentially what Kaufman was saying is, I have refuted the work of Einstein and the related work of Lorentz as well. And then people reject the hypothesis and go with the experimental data and try to come up with something new. In many cases, that's not how it works at all. And part of it is that any given experiment is loaded with, sometimes the term is, I was going to say loaded with theory, but is theory-laden. Because if you think about it, any physics experiment, modern physics experiment certainly, has very complicated equipment. You need theories about how the equipment is actually working, how whatever you're observing is actually behaving within that equipment, and so on and so forth. So there are all kinds of ways, subtle ways, where experimental results can be wrong besides just mismeasuring something like that. And so it's just something to remember that science is never quite as simple as we make it out to be. And in fact, you may remember back in week 1, one of Einstein's quotes that we highlighted, he said, "Science is something coming into being as a goal is just as subjectively psychologically conditioned as are all other human endeavors." Not speaking specifically to a point like this, but it's a good reminder that there's a lot of leeway in things like this, and things are often not quite as cut and dried as they might seem. So, role of a seemingly crucial experiment, yet in the end is experiment that was shown to be wrong, and Einstein and Lorentz in this case were correct. Another example of a crucial experiment we've mentioned before would be the 1919 eclipse expedition results. This was to test the idea that light actually bent, starlight going around the sun. So again, the idea is something like this. If this is the sun here, here's Earth here, we'll say, okay, here's Earth, this is the sun, obviously not in the scale there, and you have some stars over here, okay? And when the sun's not there, okay, so when the Earth is over here, we can observe that star, which of course is going to be way out there, and it's in a certain position. But when the sun is between the Earth and the star, if Einstein is correct, then the gravitational field of the sun, as we argued, that light will actually be bent. And so the starlight, instead of just going in a straight line like this, will actually take more of a curved path to the Earth. And so what that means is that when the sun isn't there, so another time when they measure the exact position of the star, it will actually, if you think about it this way, it looks like on Earth that the star is right here. So when the star's light is bent by the gravitational field of the sun, it seems to shift position, its apparent position, whereas another time when the sun wasn't there, it would be measured in its correct position. But because it's bent like this, we see it in a slight shift of position. Now, it's a very subtle shift here, and very difficult to measure. And of course, as we mentioned, to measure this, you need a total eclipse of the sun, because otherwise the sun's light just washes out the starlight behind it. And so that's what they did in the 1919 eclipse expedition. The British sent a team to South America and also the west coast of Africa. And here again, you have to appreciate the difficulties of measuring something like this. It wasn't like, let's just take the photographs with our equipment and then it'll be very clear. But very subtle things, just shifts in the tripod a telescope could be set up on, differences in temperature that would affect the telescope just slightly, could cause shifts in just the image of the star that would wash out the actual effect that they were trying to see. And so once they even had the data, assuming the data was pretty good, and even that, sometimes you had clouds, of course, during the eclipse, you had trouble getting good star images, sometimes they're a little blurry, and so on and so forth. And then you have to actually analyze the data and decide, is that data point good? Do we trust that data point? Or maybe that's really skewed in some way. Maybe there was a systematic error in that image, and so on and so forth again. So even though the Eclipse expedition came back and essentially said in a very famous announcement at the Royal Society in London that Einstein was right. There was sort of a lot of human factor behind that. And if you look really closely at the data, it wasn't quite as unequivocal as it might seem. So again, here's a case of something that was taken as a crucial experiment in favor of Einstein's theory, and people basically accepted it because in the end, actually, it did turn out to be correct. Another example of a crucial experiment that people did not accept, and again, at least Einstein did not accept, and Einstein was right in that case. Other times, though, Einstein himself was wrong about things like this. So just have to realize that it's a much more complicated situation than often is presented in sort of the textbook cases of these things. And the general theory of relativity predicted other things besides the bending of light. It predicted or demonstrated that certain anomalies in the planetary orbit of Mercury could be accounted for by the general theory of relativity and weren't accounted for by Newtonian theory. So there are other things going for it as well. But even when Einstein won the Nobel Prize, the 1921 Nobel Prize, awarded in 1922, as I mentioned, it was not given for any aspect of relativity because it was still fairly controversial at that point, and many people were not sure whether it really was a good and correct theory or not. So just a few comments on the role of crucial experiments there. Now let's do number 2, the nature of genius. Books and books, of course, have been written on this. Scientists themselves tend to shy away from terms like this. Most physicists, of course, are very, very smart, and yet they do recognize sort of hierarchies. But it's usually, they can say, well, that person over there is definitely smarter than I am. I could imagine being as smart as they were. But sometimes there's just this qualitative difference. It's, in modern physics terms, a quantum leap above what everybody else seems to be. And there seem to be a few scientists, a few physicists who fit in that category. What are their characteristics? Just their originality, their creativity, their imagination. And you see all of that, of course, in Einstein's work. Just their thought processes almost seem to be such that you can't imagine how they came up with an answer. What's going on inside their heads. And Einstein was like that at certain points as well. Just his whole goal, his vision of thinking God's thoughts after him, in a sense. And yet this idea of a genius, almost like a magician-type genius, where again you see these things, they come up with these ideas, and you just can't imagine where they came from. Einstein himself shied away from that. And interesting enough, you can think of Einstein sort of, even though in a real way he was a revolutionary, he was at the beginning of the quantum revolution, as we've mentioned before. He clearly, the development of the theory of relativity was revolutionary, both the special theory and the general theory. And yet, in a sense, you could say he was a conservative revolutionary in some ways, because he sort of had one foot in each camp. He went back to the classical theories. Remember how he started off with the special theory of relativity? He was very concerned about some asymmetries in Maxwell's classical theory of electromagnetism. That's what bothered him. And so he wanted to go back and fix some of those things, be true to the older theory, and out of that, though, came a real revolution. And he also was conservative in the sense that even though he'd started at the beginning with some of the ideas of the quantum revolution, as we mentioned before, he rebelled against it or went in a different direction later on in his career. So a conservative revolutionary, maybe a revolutionary conservative, if you want to think about it like that, both with one foot in the classical realm of physics and another foot in the more modern realm of physics. And other people put it like a reverential rebel. Walter Isaacson has a very good biography of of Einstein. If you're interested in reading more about all of his life and work, that's a good one to pick up. Now, I will be giving you a list of books here in one of the handouts, so you'll have that among those listed. So, the nature of genius is hard to pin down sometimes, but certainly some of the key traits we've mentioned, originality, creativity, but there's also a single-minded passion that is involved from an early age. You see this, and Einstein certainly had it, to, again, sort of think God's thoughts after him, to figure out what the world was made of and how it worked. And because he had that passion, that drive, it enabled him to, or impelled him to put in a lot of time thinking about it. You may have heard of something called the 10,000-hour rule. When they actually study geniuses and exceptional individuals, they wonder, how did they, especially young people, how did they get so good at such an early age? They found that in many cases that they certainly had, and the third factor here we'll say is talent. They certainly have talent in areas, but a lot of people have talent and don't develop as much. But it's a combination of this passion that drives them to invest the time that, combined with the talent, then takes them to higher levels than many people reach. So a number of different factors that go into the nature of genius, as it were. Okay, so just a few words on the nature of genius. And let me just say one other thing. I think I mentioned this before, but the common story that Einstein failed math, wasn't good at math, and so on and so forth. He was very good at math. He taught himself calculus early teenage years, 13 years old, 14 years old, something like that. Later on in his life, he lamented that he wasn't as good at math as he needed to be, especially for the general theory of relativity. So he leaned on certain mathematicians, in fact, his friend Marcel Grossman from his student days, who became a professor of mathematics, helped him out. And so that's why he sometimes would say, a little girl once wrote a letter to him lamenting her struggles in math, and he essentially wrote back and said, if you think you have problems, I have even more problems with math than you do. So that may be how those stories get started. But he was very, very good in science and math from an early age. Okay, number 3, relativity versus relativism. A common misconception among many people, they equate the theory of relativity with the philosophical concept of relativism. That sometimes you hear, the theory of relativity, Einstein proved that everything is relative. And this is really an ironic misunderstanding, because as we talked about, in a certain sense, the theory of relativity is a misnomer. It could very easily be called the theory of invariance, because it's built on the idea that certain quantities are invariant. And the classic example is the speed of light. It's the same for all observers, no matter what reference frame you're in. And so that's clearly the opposite of the philosophical theory of relativism. But really, there's no connection at all between Einstein's theory of relativity, special theory or general theory, and the idea of relativism, even though they often get conflated, and that sometimes impels people to rail against Einstein and the theory of relativity because of that. So relativity versus relativism. Number 4. Last one for our final comments. Besides, again, we'll do some summary comments in another video. And this is a question: Is this all really real? When we talk about things like time dilation, do moving clocks really run slow? How do they move slow? Do moving objects like sticks, does their length really contract? Do they really get shorter? Or do they just appear to do that? And sometimes you even see physicists take that tack. There's still some debate about this, but I would say the best answer to this is yes. If the measurement of time and length and things like that has any meaning at all, then yes, these are really real effects. And of course, we can see them in the experimental results. We talked about the case of the muon coming down from being created by cosmic rays in the upper atmosphere and then getting down to the surface of the Earth. You can't explain how they get down here, given such a short lifetime, without the special theory of relativity. Or the GPS navigational system. you can't explain how that works. You can't even design the system without using the special theory of relativity and the general theory of relativity there. Particle accelerators as well. High-energy particle accelerators, like the one in CERN, the French-Swiss border is where it is actually. You can't design those things and get them to actually work without the special theory of relativity. So, yes, they are really real effects. Again, the theory applies to everyday experience, but because our speeds are so low, our common everyday speeds are so low, we don't observe the effects of relativity at all. And also, sometimes you think, well, relativity and quantum mechanics, they're separate from each other, and quantum mechanics really is the more modern theory and has a wider coverage of things. Actually, in quantum mechanics, relativity is built into it. It was developed in late 1920s, early 1930s, was put into a relativistic form. And so all the modern theories of physics that deal with particle physics and things like that have relativity built into them. And therefore, it's possible that we could come up with an experimental result, or really probably a series of experimental results, that called into question whether relativity was true, but we haven't so far. Everything has been consistent. And even if we did find something, it would probably be a very small type of correction. So, yes, it is really real. And going back to one of the original quotes we started off with in terms of the course, that the special theory of relativity, in Einstein's words, is part of the marvelous structure of reality. So let's summarize week 8 now, the key topics we've covered. We start off thinking about traveling the galaxy, taking our twin paradox analysis and applying it to the possibility of a trip to the center of our galaxy, approximately 30,000 light years away, which would seem, even at the speed of light, it would take 30,000 years to get there. So it would seem totally impractical to do that. And yet, using our twin paradox analysis, which of course is based on time dilation, length contraction, the relativity of simultaneity, we showed that for the person on the rocket, if they could get up to a high enough speed, which would be very close to the speed of light, then they could even reach the center of the galaxy in 2 years and then come back roughly in another 2 years. So that was good news in a sense. It would be very interesting to take a trip like that. The more sobering news, however, is that when we thought about the energy actually involved to do that, not to mention the practical consequences of how do you take enough food along and so on and so forth, but we talked about the famous equation, Einstein's famous equation, equals mc squared, the more general form of it being equals gamma mc squared, and we saw that when we reduce that for the low velocity limit, 0.1 c or below approximately, it turned into equals mc squared, the famous part of the equation, plus a kinetic energy part. And so we identified the mc squared part with the energy associated with mass, that somehow mass and energy are equivalent to each other, and one can be turned into another. And so we gave them the usual examples of nuclear fission and nuclear fusion, talked a little bit about that in qualitative terms, how that relates to equals mc squared there. Then we turned our attention to the general theory of relativity, just a few of the foundational concepts there. We talked about Einstein's, what he said was his happiest thought, his most fortunate thought of his life, and that came in 1907 when he realized that essentially being in an accelerated frame of reference, such as if you're in an elevator that's accelerating upward, that is equivalent to being in a gravitational field, being in that elevator just on the surface of the Earth and feeling the force of gravity pulling you down. And using that, what became known as the equivalence principle. So again, we have the equivalence of energy and mass from here, but this is a different equivalence principle, and that is the equivalence of an accelerated frame of reference, being in an accelerated frame of reference, in other words, you're accelerating, and a gravitational field. And what that allowed Einstein to do was to do thought experiments, especially in an accelerated frame of reference, like an elevator accelerating upwards, and derive certain consequences of that and then say, well, because of the equivalence principle, it must be the same way for a gravitational field. And these were his initial forays into what became the general theory of relativity. And we pointed out two consequences of this equivalence principle, the qualitative derivations of them. One is gravitational time dilation. In other words, that in a gravitational field, because we showed this for an accelerated frame of reference, that a clock up here versus a clock down here, okay, this clock, the bottom clock, closer, really feeling more gravity, as it were, would run slower than this clock. Right? Or clocks higher up in a gravitational field will run faster than clocks lower down. And so that was one result that came out of the equivalence principle. Second result, again using sort of an elevator analysis, was that light would bend in a gravitational field. So those two results came out of this idea of the equivalence principle. And then we went on to talk about just several final comments. One of those was the idea of crucial experiments. The popular idea of science is you get an experimental result. If it's against a theory of the time, then you must throw the theory out. But we pointed out that theory is built into experiment as well, the theory-ladenness of experiment. So in many cases, you're not quite sure what's wrong. And so we cited the example of experiments by Walter Kaufmann of Germany right about the time of the miracle year that essentially disproved Einstein's version of the special theory of relativity and Lorentz's related version as well. And the data seem to be good. The results seem to be good. Max Planck pointed out a few things where it's not quite as clear-cut as maybe Kaufmann made it out to be, but still they were concerned that, what are you going to do, Einstein, with this? And Einstein's response essentially was, I'm going with my theory, because my theory is based on very fundamental general principles, and these experiments and some of the alternative theories they seem to support were more ad hoc in nature, not as general, and so on and so forth. And it turned out a few years later, about 10 years later or so, that as they continued to do more experiments, that there were some flaws found in Kaufmann's earlier work on this. So that was one crucial experiment where it was rejected. The results were rejected and turned out to be right. Another example were the 1919 eclipse expedition results that seemed to show, that did show, the bending of starlight in the around the sun, in the gravitational field of the sun. The question was whether the bending actually matched up with Einstein's prediction or not. And again, we cited it to indicate the human element of some of these things, because you have to, in data analysis, you have the data there and you go, do we throw out that data point because we think it's bad, something went wrong with that measurement, or maybe we keep it in because we think it's a good measurement, it just doesn't fit what we think it should be, and so on and so forth. So in the end, they did announce in 1919, the British expedition led by Arthur Eddington, that it was in favor of Einstein's theory, was confirmation of Einstein's theory, and that really was the beginning of Einstein's rise to fame, not only in the scientific world, which he had been fairly well known before that, but in the general public, in the realm of the general public as well. So crucial experiments. Said a few words about the nature of genius. One of the things we mentioned was it's the combination of passion plus time spent on task and going deep into a subject, plus talent. So it's not just talent, it's not necessarily just time, it's not necessarily just passion, but it's a combination of those, and to a certain extent being in the right place at the right time. Einstein came together with his background, his upbringing, the things he was passionate about and thinking about, and the insights he was able to generate from all that in a way that we would call genius, and it matched up with some of the key problems of the time, and he was able to make progress there. Later on in his life, he wasn't quite as successful, although he did certainly for the next 20 years or so after 1905. He seemed almost every couple of years he'd come up with a new result. Even things we didn't get a chance to talk about in this course, but even modern day things like lasers go back to some of the theoretical work Einstein did in the early part of the 20th century. So Einstein's fingerprints, as it were, are throughout modern science, not only in relativity, but also in quantum mechanics and in many other ways as well. So that was a few words on the nature of genius. And then relativity versus relativism. We noted they're very different things, although people often confuse them. And in fact, somewhat ironic misunderstanding, because relativity really is a theory of invariance, the unchanging quantities, while relativism as a philosophical theory says everything's relative and everything changes in a sense that way, or you can't choose between things, as it were. And then finally, just ask the question, is all this really real, this time dilation stuff and length contraction and the twin paradox and everything else? And we said it actually is. It is part of the marvelous structure of reality. One of the original quotes we quoted from Einstein, that it's the way the world works. We have good experimental evidence for it from, we cited the example of muons, the GPS navigation system, particle acceleration, so on and so forth. None of that makes sense without the underlying foundation that Einstein provided with his special theory of relativity and then later on his general theory of relativity. For our final video of the course, let's try to recap some of the key concepts and principles we've covered, sort of like our roadmap or our journey through the course. Obviously, it won't cover everything. It's a challenge just to get all on one board, but I think we got it all on here without squeezing it too much. So remember, we started off just talking about Einstein in context, which meant looking at the scientific background of his time, some of the key scientific discoveries and developments throughout the 1800s. Einstein being born in 1879, of course. Also the technology of the time, because remember his family was very involved in electrotechnology, and of course later on he worked as a clerk at the patent office, and so saw a lot of the things that were going on in terms of, especially things like synchronization of clocks and other things going on in electrical technology of the time. We can't draw a direct connection between those things to some of his work, especially in the special theory of relativity and the relativity of simultaneity and clock synchronization, as we talked about. But it's certainly part of the environment there, and it may have in some way inspired his thinking on some of these matters. So both the science and the technology of the time is important. We talked about 1905, his miracle year, some of his early struggles as well, if you read the Young Einstein article. So we talked about the key papers in the miracle year, with a focus, of course, on the June 1905 paper on the electrodynamics of moving bodies, which is what we know as a special relativity paper. We also noted that what really bothered him were certain theoretical asymmetries in terms of what was going on. We talked about some of the experimental results, especially the Michelson-Morley experiment and stellar aberration. They did not seem to have as big an influence on Einstein's thinking as just some of the, again, as he termed it, the asymmetries involved. We talked about the bar magnet and the coil of wire, and how, depending on which was considered to be moving, physicists had one explanation for one scenario, another explanation for another scenario, and things like that really bothered Einstein, to the point that he described it as, after years of thinking about this, by this time being 26 years old, it was almost a state of psychic tension for him. And then out of that, through some conversations with his friend Michael Besso, you may remember his flash of insight that time was suspect, as he later termed it. So what he then did is he took two key principles that were well established in physics. One, the principle of relativity. So we spent some time talking about Galilean relativity and just the basic principle of motion of objects and how you can convert from one frame of reference to another frame of reference if they're moving at a constant velocity with respect to each other. Talked about that a little bit. And the other principle was what he termed the principle of light constancy, that the movement of a source of light, or really a source of waves, means that it's not going to actually affect the velocity of the waves coming out of that. So we spent some time just talking about how waves work to get some background on that and understand this principle of light constancy. And then also the conflict between them, because the principle of light constancy implied that an ether existed, and it was just assumed that you had to have some sort of medium for, if light was a wave, you had to have some sort of medium through which it traveled, and the idea was that it was this thing called the ether, and so they spent a lot of time creating models of the ether, wondering about how it might work, be put together, and so on and so forth. And the problem with that, though, is that it went against the principle of relativity, because if you had an ether, you could assume the ether was the absolute reference frame. And so you could have absolute motion against, measured against the ether, or just a state of absolute rest would be the ether, the underlying foundation of the universe, as it were. And so Einstein saw this conflict here, and he said his insight was, actually, they're both true here. And out of those two principles, then, we showed that you get the invariance of the speed of light. That combine those two things together, it's not just that if you have a moving source, the light coming from that moving source has a constant velocity, an invariant velocity, but it's any motion at all. One observer to light, or to another observer moving with respect to light, speed of light will always be the same to all observers. And that came from the combination of these two seemingly incompatible principles. So that was Einstein's key insight that set him off on this path. And then from that, we looked at, okay, what do we get out of that? Well, one key thing was the so-called relativity of simultaneity, that clocks synchronized in one reference frame will not be synchronized in a moving reference frame. We talked about the concept of a lattice of clocks for each reference frame that would be synchronized. And so the relativity of simultaneity, or the relativity of clock synchronization, that that was a big news for the time, because the standard assumption was, well, of course, everybody measures the same time. Time is absolute. It doesn't matter how you're moving with respect to somebody else's clock. You'll see the same time as they will. But Einstein showed, and we sort of followed in his footsteps here, that put these two principles together, accept both of these well-accepted principles, and even though they seem to be in conflict, you get, if you accept them as true, you get the relativity of simultaneity. And from that, then, other results tumbled out. We talked about time dilation using the light clock example, again coming from the invariance of the speed of light, so that a moving clock, an observer who observes a moving clock will observe it to tick more slowly than an identical clock that he or she has next to them. So time dilation. And from that, we also got the Lorentz factor gamma, the scaling factor for time dilation, really. And then from that, we get length contraction as we analyzed it further, that moving objects contract in the direction of motion to an observer who is observing the moving object. If you're riding along with the moving object, of course, everything in your frame of reference, everything is normal. It has its normal length because you're in its so-called rest frame. So it's rest length or proper length. So time dilation, the Lorentz factor gamma, length contraction. I won't write down the formulas here because you should know them by now. Of course, you can quickly remind yourself, review that. The invariant interval, I actually did write down this formula just to remind us. That also came out of an analysis of the light clock thought experiment, and we showed that for all observers, this combination of things from one event, two events in one frame versus another frame, c squared, t squared minus x squared will always be constant, and allowed us to do a few calculations with that. And then the phrase leading clocks lag, that we talked about the relativity of simultaneity, relativity of synchronization, but that if, as you observe two clocks go by, and they're moving with respect to you, the leading clock will lag behind the trailing clock. And that was a key result we did both qualitatively and then later quantitatively once we had figured out the Lorentz transformation. And that was probably the most complicated analysis we did, mathematical analysis we did, the derivation there, but we got that such that we could transform between different inertial frames of reference very easily. If, again, Bob and Alice, if Bob measured a certain event in his frame of reference at a certain position and a certain time, if we knew that, and we knew then the velocity between his frame of reference and Alice's frame of reference, we could very easily figure out where would that event occur in space-time analysis frame of reference. So that was why the Lorentz transformation became handy to do things like that. And of course, we talked about space-time diagrams. We actually introduced them back here when we talked about relativity, but we made use of them in terms of Lorentz transformation, getting both frames of reference, as it were, onto the same plot, and did a few things with that. And then just looked at some of the famous implications of all this. Not that time dilation, length contraction aren't famous in and of themselves, but we considered the situation, can you have faster than light travel? We did one example where we had the spaceship going from San Francisco to St. Louis to New York, and showed that actually in that case it's an optical illusion that you get faster than light travel. The spaceship never goes faster than the speed of light, but it seems like to an observer in New York, say, that things are traveling faster than light. We looked at cause and effect situation where if you do have faster than light travel, you get a reversal of cause and effect, which is a strong argument against the possibility of faster than light travel, because we just don't see things like that happening. The universe doesn't work that way. There seems to be a definite chain of cause and effect. Although, of course, in quantum mechanics, it gets a little more complicated than that. But even in quantum mechanics, you don't have you don't have time running in reverse, essentially. At least in experimental situations. In theoretical situations, you can actually imagine time running in reverse, but that's a whole other topic which we didn't get into. So we definitely show the cause and effect that if you have faster than light travel, you can have something happening actually before its cause. And we did the example of the spaceship traveling away from a planet, and then the good guys traveling away, and the bad guys inventing a faster than light spaceship and traveling after them and actually destroying them. In the good guys' frame of reference, they get destroyed before the faster than light spaceship is even invented. So we say there's a contradiction there, and therefore can't happen. So more implications, of course, paradoxes. We talked about the pole in the barn paradox. We talked about the spaceships on a rope paradox. And, of course, we talked about the twin paradox. And then that led us on to, in the final week, talk a little bit about galactic travel. Is it possible, especially given the results of the twin paradox? In principle, it is, that you can travel to the center of the galaxy in a reasonable amount of time. If you're on the spaceship, though back on Earth, thousands of years will pass by. But then we ran into a problem when we considered the famous equation E equals mc squared, or the general form of it, E equals gamma mc squared. We discovered that the amount of energy to get up to the speeds needed, very close to the speed of light, to make galactic travel possible, even in just theory, is far more than we certainly know how to get at this point in time. And then finally, just a few words on general relativity, the equivalence principle between accelerating frames of reference and gravity, and therefore that led on to showing that actually in a gravitational field, time dilation occurs. And we mentioned this is a factor in the GPS navigation system that has to be taken into account, that satellites are up here and we're down here, and therefore satellite clocks will actually run faster than clocks here if they're identical down on the surface of the Earth. So that has to be that time. It's not really a time delay; it's a time dilation factor. You have delay of speed of light signals moving from one to the other, but in addition to that, you have just simple time dilation. The clocks on the surface of the Earth will run more slowly than identical clocks on the satellite. So that has to be factored into the system, and the bending of light in a gravitational field as well. So a lot of things we covered. Amazing, actually, we can sort of get it all on one board, at least the key concepts here, so you can see where we've come. Hopefully that helps you get a big picture view, because again, sometimes we get so caught up in the details we lose sight of where we've been and where we might be going with it. But I hope as we start off the course, one of the key quotes, we talked about not only the mystery of the marvelous structure of reality, we mentioned that several times now, but also Einstein's quote to the point that just the struggle to understand, and yes, it certainly is a struggle to understand a lot of these things, whether in the details or just even the big picture concepts as well, but that the struggle to understand can be an ennobling experience and even an enriching experience. I hope you found some of that as we've journeyed through this course together.